Greetings. We considered the coupling of angular momenta J1 and J2, and we recognize that each of these has got a vector representation in a basis which is 2j plus 1 dimensional. So, there is a 2j1 plus 1 dimensional basis for J1 and a 2j2 plus 1 dimensional basis for J2, and the uncoupled basis will have a product dimension of 2j1 plus 1 times 2j2 plus 1. These spaces are individually completely disjoint, they have no common parts, because angular momentum J1 and J2 are completely independent of each other. Each component of J1 would commute with each component of J2. Okay? And we are now composing from these individual spaces the product space, and the product space will be the composite space which is made up of the individual spaces of J1 and J2, right. So, now if you look at the left hand side, which is the net angular momentum coming from the sum of these two, and this is a new type of sum, this is not just the vector addition, because it is an addition of two quantum vector operators. We certainly expect that this space of the coupled angular momentum will have the same dimensionality as the product space, because it is coming from that. So, we anticipate the answer to be 2j1 plus 1 times 2j2 plus 1, but that is not obvious from what we are looking at. The only thing we know from this, that this j will have 2j plus 1 degeneracy coming from the isotropy, right. So, it will have m quantum number which will go from minus j to plus j. So, there will be a 2j plus 1 dimensionality that will come from that, but that will have to be compounded by some additional factor which is coming from the values that j can take, because we have to find out what kind of values j can take, and that will give us the net dimensionality of the coupled angular momentum. So, the coupled angular momenta I am representing by these curved brackets, and the uncoupled by angular brackets, that is just for convenience. Now, this we know that m can go from minus j to plus j. So, there will be 2j plus 1 values. J quantum number j, this will have a certain range from a minimum to a maximum, but we do not know exactly what this value of minimum is and what is the maximum value is. That is something which we probably know from some of the other courses, and we perhaps know it from some literature that we have read, but we are going to determine exactly what this value of j min should be, so that it will not be an assumption in our minds. So, we will find out what j min can be and what j max can be, and it will turn out that the minimum value is modulus of j1 minus j2, and the maximum value will be j1 plus j2, and we will prove this particular inequality that we have in front of us. Okay. So, essentially we are dealing with alternative orthonormal basis sets. One is the basis of the uncoupled vectors, which is the direct product of uncoupled vectors. So, these are the angular kets, and you can compose the product basis. In brief, you can suppress the notation j1 j2 and simply write these as m1 m2. So, this is the m1 m2 basis, and then you also have the alternate basis, which is the eigenbasis of the coupled angular momentum, which is j, and this is the eigenbasis of j square and jz, these two operators, since they commute with each other. Okay, these are the two simultaneously diagonalizable operators. So, you can consider transformations from one basis to another, because an arbitrary vector you can always express as a linear superposition of any basis set, it does not matter which it is. So, let us represent this coupled vector which is written here as well, but it is operated upon by the unit operator, and I have decomposed the unit operator. This is the resolution of unity as we call it, in the basis of the product of uncoupled vectors. Okay, M1 M2 are the product vectors from the uncoupled basis. So, this is the resolution of unity, and you find that this expression amounts to a linear superposition of these M1 M2 vectors scaled by these scalars that you find in this bracket. This bracket has got an angular bracket on one side and a curved bracket on the other, but essentially it is a bracket, it is a scalar, and whether it is angular or circular is just a matter of a convenient notation. There is no big physics in it, it is just a scalar, and these scalars are known as the Clebsch-Gordon coefficients. In general, these can be some complex numbers, but they turn out to be real, as we will see, and these are the Clebsch-Gordon coefficients. You can write them in the complete notation inclusive of the J1 J2, and this is the coupled vector Jm coming from J1 J2, and you can insert the J1 and J2 quantum numbers on this side as well, just for completeness. So, here we have this expression along with the Clebsch-Gordon coefficients, either in the brief notation or in the complete comprehensive notation. Again, some books write J1 J2 over here and then M1 M2, some other books write J1 M1 and then J2 M2. So, this is just a matter of choice. The actual physical content of both of these notations is exactly the same. So, sometimes different books on quantum mechanics, Merzbacher, Schiff and so on, they use slightly different notations. So, no big deal about it, just keep track of what is the physical content which is going into the labels. So, you now construct the inverse transformations. We had expressed the coupled vector in terms of the uncoupled product vectors. Now, we do the inverse transformations, and on the left hand side we have got the product of uncoupled vectors, which is now expressed in terms of the coupled vector, because you can simply pre-multiply the same vector M1 M2 by the resolution of the unit operator, but this resolution is now carried out in the coupled basis. Okay? And therefore, what you find over here is an expansion in terms of the vectors of the coupled angular momentum, and then again you have coefficients which play a similar role as the coefficients that you saw earlier. So, they are again the Clebsch-Gordon coefficients, and you know that in this basis set M will go from minus j to plus j, that is coming from isotropy of space, because the axis of quantization can be anywhere, right. So, you have a 2j plus 1 fold degeneracy coming from the M Compton number, and the j itself will go from a certain minimum value to a maximum value, and what we are going to prove now, that this minimum value is the modulus of J1 minus J2 and the maximum value is J1 plus J2. So, that is what we are about to prove now. Okay. So, let us see how the proof goes. So, this is the coupled angular momentum, and this again you can write in alternative complete notation, either by writing J1 J2 in a parenthesis over here, or spread it out fully in this product vector. So, this is just a matter of notation, and I like to highlight this because you use different sources of books on quantum mechanics. So, you are going to find all of these notations. So, our proof is going to be based on a few factors, and the first thing we do is to prove that the Clebsch-Gordon coefficient must have this M quantum number to be equal to the sum of these two M quantum numbers. That is a necessary condition for the Clebsch-Gordon coefficient to be non-zero. Now, this proof is a very simple one. It comes from the simple consideration of the fact that you simultaneously diagonalize j and j square, j square and jz or j dot u in some direction, and you can therefore construct an eigenvalue equation for jz. And now over here in between you can sandwich the unit operator. That is one thing that theorists can do very freely, which is always insert a unit operator and resolve it. Okay, that is the resolution of unity. So, you sandwich a unit operator so that you express it as a linear superposition of base vectors in the uncoupled basis. This is the product of uncoupled vectors, uncoupled angular momentum eigenstates, right. So, this is one expression that you have for the result jz operating on Jm. Now, you can expand these terms further. I have written the J1 and J2 more explicitly over here. This is a direct product of these two vectors, which is J1 M1 and J2 M2. So, essentially you have got these two operators J1Z and J2Z operating on this direct product, and there are two terms, one coming from J1Z and the other coming from J2Z. So, you can get these two terms by explicitly carrying out the operation by J1Z plus J2Z on this product J1M1 J2M2. So, that result is quite simple. You will have J1Z operating on J1M1 and J2Z operating on J2M2. So, these are the two terms. So, you have written this entire double sum as a double sum of two terms. So, this is a fairly simple simplification of this expression. Now, what is J1Z operating on J1M1? It is of course M1 H cross times J1M1, right, and J2Z operates on J2M2, which is this vector over here. It does nothing to J1M1 because J1 and J2 are completely independent angular momenta. That is what I meant when I said that the two individual spaces are completely disjoint, they have nothing in common. So, J2Z will do nothing to J1M1, but it will operate on J2M2, giving you the eigenvalue M2 H cross, and now you can sum these two terms because both are summations over the same base vectors M1 M2, one scaled by M1 H cross and the other scaled by M2 H cross. So, extract H cross as common and you have got a factor M1 plus M2 times H cross. So, this is a linear superposition of these base vectors scaled by appropriate coefficients, and these coefficients are H cross times M1 plus M2, and do not forget the Clebsch-Gordon coefficient, which is also there. Okay, so, that is also involved in the scaling. So, that is the right hand side. Left hand side is very simple to resolve because Jz operating on Jm gives you an eigenvalue equation, and you can express this term once again by inserting a similar unit operator. So, that both on the left hand side and right hand side you have got linear superpositions and basis sets which are exactly the same. Okay, then you can always extract the coefficients of corresponding terms. Okay, that is the idea. So, let us do that. So, you have got Jz operating on Jm, which gives you mh cross times this whole sum, and now if you compare the coefficients, you have got two expressions on the right hand side, both being equal to the left hand side, which is Jz operating on Jm. Both this term as well as this term are expansions in the same basis sets, which is M1 M2 basis. They have got the same factor H cross which is common in both. This scalar the Clebsch-Gordon coefficient is also common in both, and now you have got m1 plus m2 is one factor here which must correspond to the factor m over here, because whenever you have expansions in linearly independent basis, and if you have two such expansions which are exactly equal to each other in the same orthonormal linearly independent basis, then the coefficients of the corresponding base vectors must be necessarily equal. Okay. So, that is a fundamental theorem that we make use of, and we find that m must be equal to m1 plus m2 in every Clebsch-Gordon coefficient. Okay, that is good. Now, we will proceed to establish what the minimum and the maximum values can be like. Now, this is what the result will turn out to be, and to do that we now have a look at the Clebsch-Gordon coefficient and just see its terms. So, this is the full notation for the Clebsch-Gordon coefficient, this is the brief notation in which I have suppressed J1, J2. What we do know in this is that m must be equal to m1 plus m2. Okay, that is something we have already established, and we will use that result. Now, we use a particular Clebsch-Gordon coefficient now, a particular one in which m1 takes its maximum value, and there is no ambiguity there. We know that the maximum value that m1 can take is J1. We also pick the maximum value of m which must be j, there is no ambiguity about this either. We know that the maximum value m can take is j, we do not know what is the maximum value of j, but we do know what is the maximum value of m. Okay. The maximum value of j is what we are yet to determine, which we are about to determine, we do not know that as yet, but the maximum value for each value of j is known, that is m. So, that is what we take. So, now we consider such a Clebsch-Gordon coefficient for which this m1 is equal to j1, this m is equal to j. So, this jm becomes jj because m is equal to j. Okay. m2 is whatever it can be, but it can only be m minus m1. Okay. So, we do not put any constraint on m2 externally, but it does have its own constraint that it has to be m minus m1. So, we will exploit that. So, m2 can be only m minus m1, otherwise the Clebsch-Gordon coefficient does not exist. So, now we know that this m2 will be m minus m1, but m has taken its maximum value which is j, and m1 has taken its maximum value which is j1. So, this value m2 is j minus j1. Okay. Now, that is good because this is the value which m2 takes, but you already know that the number of values m2 can take will be 2j2 plus 1, and they will range from minus j2 to plus j2, that is known. Okay. So, this m2 which can belong to this range minus j2 to plus j2, this m2 being what j minus j1 is, you now have j minus j1 to fall in a certain range which will have the lowest value to which it can be equal. So, this will be the minimum value which is minus j2, and the maximum value will be j2. Okay. Now, all you do is to add j1 to every term in this inequality. So, now you have got j1 minus j2, here you add j1. So, j minus j1 plus j1 will give you j, and now what you find is that j belongs to this range. Okay. Now, what is special about 1 and 2? What we called as 1 we could have called as 2, and what we called as 2 we could have called as 1, right, or you could begin with the other way around. So, anyway what you essentially have is that you have got a certain number of values which M2 can take, and that number we know very well must be 2J2 plus 1 values, and these are the values that can be taken by whatever appears in the middle term of this inequality, which is J, right. The middle term can take 2J2 plus 1 values. Likewise, we have now found that J can take 2J2 plus 1 values. So, remember this result, and this is something that we are going to use again in a very important but simple step. If we had called 1 as 2 and 2 as 1, or we could have begun first with the maximum value of M2 and the maximum value of M, and then find what would be the maximum value of M1, right. What are the values of M1 that could be taken, we would get an exactly identical result, that J2 minus J1 would be less than or equal to J less than or equal to J1 plus J2. So, these two expressions both are completely equivalent and both must be satisfied. So, J1 minus J2 must be less than or equal to J less than or equal to J1 plus J2, and J2 minus J1 should also be less than or equal to J less than or equal to J1 plus J2. How can both be true? They can both be true if and only if you take the modulus of J2 minus J1. Okay? So, your expression will have to have this constraint. Your inequality will have to be that the minimum value will not be J1 minus J2 or J2 minus J1, it will depend on which one is larger. Okay? So, it has to be the modulus of this difference, because if one of them is larger than the other, you will get into trouble, and you must have both of these inequalities to hold. So, you can satisfy both the inequalities by requiring that the modulus of this must be less than or equal to J less than or equal to J1 plus J2. So, this is a very nice result, and it is called as triangle inequality, because if you look at the sides of a triangle A, B and C, then you have this inequality between the three sides. Okay? The modulus of the difference between these two sides will be less than or equal to the third side, which will be less than or equal to the sum of the other two. So, that is the reason this is called as a triangle inequality, and it is exactly the same kind of relation that you get for the angular momentum when you couple them. Okay? So, we know what is the range of J. So far so good, but we still have to get the dimensionality of the coupled space. We have anticipated a result, but we have not proved it. So, we might as well prove it. So, now that we know that the result holds good no matter which is larger of the two, and without any loss of generality, just for our discussion, we will assume that J1 is greater than or equal to J2. We will use the result from here that M2 can take 2J2 plus 1 values, and these are the number of values which the J quantum number can take. So, we know that this quantum number J can take 2J2 plus 1 values. Okay? So, we will use this result, and that is the reason this is highlighted in this yellow background. Okay? We are going to use it in a very simple but important step. So, for every J, M can take 2J plus 1 values. This is already known. So, what is the dimensionality of this space? It is 2J plus 1 for every J value. M is going to take 2J plus 1 values. J will take all values from a minimum to a maximum. The minimum is modulus of J1 minus J2, but we have assumed for our discussion that J1 is larger than J2. That is the reason I have written it as J1 minus J2 to plus J1 plus J2. There is no loss of generality in this, we have already established that. What does this sum add up to? Now let us carry out this sum explicitly, and this sum can be carried out in a number of different ways, and there are well known techniques in how you sum a series that you can use to work out this sum, but I will show you a very simple way of doing it, because it also gives you a little bit of physical insight into the whole story. You have the total number of states which will be, for each value of j you know that there will be 2j plus 1 values going from minimum to a maximum. So, I have written all of these total number of states to be given by 2j max plus 1, then max reduced by 1 plus 1, then reduced further by 1 plus 1 over here, right, and the lowest value of j will be j min, and it will be 2j min plus 1. So, this is the total number of states, right. Now, this is the total number of states, and you can now write this j max we know is j1 plus j2, j min is j1 minus j2, right, and in between the differences go in steps of 1. So, the maximum value I have written explicitly as j1 plus j2, the minimum value I have written explicitly as j1 minus j2. So, it is the same box which I have now written over here, which gives me the total number of states, and I am going to bring this box on the right hand side to the next slide and continue the analysis. So, this is the same box, we have got 2 j max plus 1 which is now 2 j1 plus j2 plus 1, this lowest one was 2 j min plus 1 which without any loss of generality is 2 j1 minus j2 plus 1, right. And now let us analyze this further, because you expand this is 2 j1 plus 2 j2 plus 1. So, I have written this as 2 j1 plus 1 plus 2 j2, this is you have 2 j1 again 2 j2, then you have 2 into minus 1 which will give you minus 2. So, that minus 2 comes here. So, this entire expression is completely equivalent to this row over here. Likewise, if you look at the next one in which this number is reduced by 1, so this becomes minus 2, and now you have 2 j1 plus 2 j2. So, you have 2 j1 here, 2 j2 is here, you have 2 into minus 2 which is minus 4, minus 4 comes here, and then you have got this 1 which is sitting over here. So, all the terms are taken care of, okay, and you see that every term or set of terms is completely equivalent to the set of terms in the next box. The lowest one is 2 j1 minus j2 plus 1 which is 2 j1 minus 2 j2, this plus 1 comes here, and this 2 it is already there, right, sorry, oh this is the one, yeah, this is the one. So, this is 2 j1 and this plus 1 is coming from here, and this minus 2 j2 is coming from this 2 into minus j2, okay. So, this is the corresponding term, good. Now, let us have a look at this. This 2 j2 plus 2 j2 cancels this minus 2 j2, they are all in the same box, they are all adding to each other, but this one comes with a plus sign, this one comes with a minus sign. So, they kill each other. Then the 2 j2 minus 2, this one comes with a plus sign and a minus sign over here, these are with opposite signs over here. So, these two terms kill each other, okay. And likewise this 2 j2 minus 4 will cancel minus 2 j2 plus 4, and they will all cancel out likewise, okay, every term, and what you are going to be left with is just 2 j1 plus 1 coming from here, 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 and all you will be doing is to add up 2 j1 plus 1 to 2 j1 plus 1 plus to 2 j1 plus 1. How many times would you do it? 2 j2 plus 1 times, okay. You will do it exactly 2 j2 plus 1 times, because those are the values that J can take. Okay. So, the result is that when you carry out this series summation, it turns out to be a product of 2J1 plus 1 times 2J2 plus 1. Okay. So, it is a very simple proof, and you know that the final dimensionality of the space turns out to be what we expect it to be, and it is not a mystery, and it is not coming just from our expectation, from your intuitive expectation that it has to have the same dimensionality, but you can actually show it by carrying out the summations explicitly and looking at the dimensionality of the space. So, now we have got the final expression for the dimensionality of the space, and we will proceed to work with the Clebsch-Gordon coefficients, and I will develop the recursion relations for the Clebsch-Gordon coefficients, because it is very nice that you can get all the Clebsch-Gordon coefficients just from one number, and you begin with that number which happens to be 1, which all of us know what it is, and from that you can get every other coefficient, but we have to see how and why this is true. So, let us look at the summation of the angular momenta, and this guarantees that if you add the corresponding step up and step down ladder operators, they will give you the step up and step down for the coupled angular momentum, and we consider the one with plus sign. Okay. There is a similar expression for the minus sign for the step down operator as well, but I will consider the step up operator and operate on the coupled angular momentum by the step up operator. On the right hand side, I decompose the coupled step up operator in terms of these components J1 plus and J2 plus, and insert the resolution of the unit operator. Okay. So, left hand side we know from what we have done earlier is given by this square root term. We have done this a number of times already. So, this is your left hand side, and you can again insert a unit operator here and then take this coefficient inside. So, we now look at the right hand side. Now, the right hand side is obtained from the operation by a sum of two operators. So, you can separate the two terms by operating by these two terms individually on this, and J1 plus will operate on the M1 part and J2 plus will operate on the M2 part, because the two vector spaces are completely disjoint. Okay. So, this product of the uncoupled vectors I have written explicitly as a direct product of these two vectors. We know what a direct product is. And now we will let J1 plus operate on J1 M1 and J2 plus operate on J2 M2, and we know that these are step up operators. So, it will raise the corresponding azimuthal quantum number respectively by 1. So, J1 plus will operate on J1 M1, J2 plus will operate on J2 M2. Over here J2 M2 simply comes out as a multiplier, whereas over here J1 M1 comes out as a multiplier, but of course there is a residual multiplier which is coming from the Clebsch-Gordon coefficient. So, that will be carried forward. So, we have this right hand side, and J1 plus when it operates on J1 M1 will raise the M1 index to M1 plus 1, and then it will scale the resultant vector by this h cross times the square root factor which we have handled earlier. You are going to have the same thing happen to the second term, in which you have the J2 plus operate on the J2 M2. So, the M2 index will go up by 1. So, here you have the M2 index go up to M2 plus 1, and then you have the h cross times the square root factor, and you do have the residual Clebsch-Gordon coefficient factor. Now this is rather interesting, both of these are summations in the M1 M2 basis, but you cannot combine them because in one the index is M1 plus 1 M2, and in the second term here this index is M2 plus 1. So you will like to combine these two terms, and you can certainly do that because both of them are complete summations. Here M1 goes from minus J1 to plus J1, M2 goes from minus J2 to plus J2. Same thing happens in the second term, that M1 goes from minus J1 to plus J1 and M2 goes from minus J2 to plus J2. So both are summations in the complete set of bases. It is going to pick every term. So instead of counting from here and then take the next term and then take this term and then go all over and come back, you can begin counting from here, take the next term and come back and pick all the terms in the complete set of bases, right. So it is like counting the number of students in the class, and I can begin with Aarti and go around, or I can begin over here and then go around. So it does not matter where you begin the counting, it is exactly that. So let us do that by shifting the index. I can get both the terms expressed as superposition over the same base vectors, but the indices must be shifted because here the index is M1 M2. In this first term you have M1 plus 1, in the second term you have M2 plus 1. So if you want to make the summations correspond to each other, you must drop this index M1 plus 1 to M1, but then you must drop every M1 by 1. So this M1 must be reduced by 1, this will become M1 minus 1. This M1 will also become M1 minus 1. This M1 plus 1 must be dropped by 1, so it must become M1. Okay. So by dropping that index, that quantum number by unity, okay, you make all the terms such that the linear superposition is over the dummy index M2 rather than M2 plus 1 or M1 plus 1. Okay. And it does not matter whether the dummy index is M1 plus 1 or M1 itself, it is exactly like counting the number of students in the class. It does not matter where you begin the counting. Okay. You can count with the next student or the one after him or the one after him, and then go back, count everybody, and then go back to the previous one. Okay. So that is exactly what you are doing, and now having shifted the indices, but in shifting must be done in a very consistent manner. So if you change this index from M1 plus 1 to M1, then in the corresponding term every M1 must be dropped by 1, and you do the same in the second term, and now you have got expansions in both the terms which are in the same running index as such, which is M1 M2, but the coefficients of course are different, and you can combine these coefficients now. So you have now combined the coefficients, H cross comes out as a common factor, the two remaining factors are combined together, which includes the square root term and the corresponding Clebsch-Gordon coefficient. This one has got M1 minus 1 over here, this one has got M2 minus 1 here. Okay. Because how did we get that? Because of shifting the indices in a consistent manner. So now we have got the right hand side expressed as a linear superposition of base vectors M1 M2, left hand side is also expressible as a linear superposition of the same base vectors M1 M2, and now you can compare the corresponding coefficients, H cross cancels, and now you have got a relation which connects this Clebsch-Gordon coefficient with this and this, in which the indices are shifted. Okay. Now this is the recursion relation. You get it? It means that the Clebsch-Gordon coefficients are not completely independent of each other, they have some relationship with the neighboring Clebsch-Gordon coefficients, and you can find what these exact values are, because there is another recursion relation that you will get by using the step down operator and using exactly the same procedure. So, there is more help available than what we obtained in the previous step. The other relation is the recursion relation that you will get, which I leave as homework. It is the same procedure, you can do it quite easily. So, these are the two recursion relations that you get, and I have combined the two recursion relations by writing this expression inclusive of a plus and minus sign over here, and there are corresponding plus and minus signs, there is a minus and plus signs. So, you get the top signs to correspond to each other and the lower signs to correspond to each other, and that is where the two relations are written together in this expression. So, these are the recursion relations for the Clebsch-Gordon coefficients. You already know that the term under the square root can be written as a product of two factors, that is just a matter of notation again, and these recursion relations are extremely useful in getting the Clebsch-Gordon coefficients and doing angular momentum algebra. So, you can write them in terms in one or the other notation, and different books make use of different kind of notations, that is just a matter of detail. So, this is the summary of what we have got so far, and we established the triangle inequality. We know exactly what the angular momentum J can be. It can take only these values, it can take a minimum value which can be the modulus of J1 minus J2 or modulus of J2 minus J1, however you like to say that, and this is called as the triangle inequality. You also learned today that the dimensionality of the basis must be 2J1 plus 1 times 2J2 plus 1, as we expected already from our reasoning that it is the same product space which is being expressed in a different basis set, which is the eigenbasis of the coupled angular momentum. So, the other thing that we did today was to obtain the recursion relations between the Clebsch-Gordon coefficients, and these are very important steps or important elements of the angular momentum algebra. You are going to find them very useful, and we will continue to use the Wigner-D matrices, okay, which are quite important, but now we are much better equipped to do that. So, if there are any questions, I will be happy to take, otherwise I will stop here today, and we will continue from this point in the next class. Questions?
So, in the slide number 135, operate that raising and lowering operator, and or M1 and M2 indices gets up by unity. But the second term, that in the second expression, you drop it by -1. When you are dropping it by -1, but in the second part, means the first sum plus the second part, but there is no, it's not changing the M1 value in the second expression. So why is it so?
Just
here?
Yes, because since it's a part of that expression, it's very.
This is a part of the expression, but the sum is here. These two sums are completely independent of each other. These are two separate terms. What happens in the first term does not affect anything in the second term, and vice versa. So, in the first term we are dropping the M1 index, and we do it consistently for everything in the first term. Okay. In the second term we drop the M2 index, but then we do not touch the first the other index, which is M1. We have to do it independently. It is not that we can, we have no choice, we have to do it independently, because the two terms are completely independent of each other. You do the counting is within each term. You have a double sum, you decompose this double sum into these two terms, right. So, this what I have over here, if you are able to see the locus of this arrow, okay, what is inside this is one term. This is what I call as T1, first term. This is now the second term, which is T2, okay, and the summation in T1 has a value which is quite independent of what is happening in T2. You have decomposed it, and then each term has its own significance, it has its own merit, it has its own strength, and the indices have got an impact within the term. A dummy sum in term 1, a dummy index in term 1 does nothing to a dummy index in term 2, but a dummy index in term 1 has to be handled consistently within the term 1, and you must do the same with the second term, that whatever is the dummy index, if you shift the dummy index within the second term, then within the second term all the corresponding indices must be shifted consistently, right. Any other question? But a good point, it is neat to know that, because you will be doing fairly complex algebra with angular momentum terms, and then it is important to do this carefully, because it is very easy to make a mistake, let me assure you that. Yes.
Sir, in each expression we are changing, first expression we are changing the m plus 1 as m1, but in the summation sign we are not changing the m1.
May not be.
It does not matter, the summation symbol is a dummy symbol, all it is telling us is that go pick every term. You can define m1 plus 1 as m1 prime, and then have a dummy index m1 prime equal to m1 plus 1. You can add one more step if you like, it is not going to change the result. All you have to remember is that it is a dummy index which must pick every value in the range of m1, and every value in the range of m1 is minus j1 to plus j1. Okay. And the example of counting the number of students in this class is really a very appropriate one, because you have to count every single term, and it absolutely does not matter where you begin the counting from. I can begin counting with Aarti or begin counting with Ankur, although Cosmic may complain, why not me. So we can start counting from Cosmic and then go back till then, right, but you are going to get the total number of students to be exactly the same. So you are picking every term in the basis set. Any other question? So thank you very much.